Hi everyone, let me welcome you to the 23rd session of ECT 204 Signals and Systems. In the last video we have learned how to compute Fourier transforms with the help of their properties. In this session we see how LTI systems are analyzed using Fourier transform. The speech is organized into your learning outcomes, output of LTI systems with a few examples and the summary of understanding. So in this video you will learn to realize the output of LTI systems in frequency domain as product of Fourier transforms. Then you will understand the input and output power spectral densities. Then you will learn to analyze LTI systems with the help of Fourier transforms. The output of LTI system is a linear convolution between the input and the impulse response. So yt, that is equal to xt convolution ht. If I take Fourier transform of either side, y of f is equal to xf into hf, because in the last class we saw that we proved that time domain correlation that appears as a multiplication in the frequency domain. So yf is equal to xf into hf, or h of f, that is equal to yf divided by xf. So HF is called the frequency response of the LTI system. It is nothing but the Fourier transform of the impulse response HT. If I take the Fourier transform of HT, I get HF, that is YF divided by XF. So if I take the conjugate of this Y conjugate F, that is equal to X conjugate F into H conjugate F. So if I multiply this equation by YF, it becomes YF into YF conjugate, that's equal to mod YF square. That's equal to XF into HF into X conjugate F into H conjugate F. So this becomes mod HF square into X of mod XF square. So by this equation, mod YF square, that is equal to mod HF square into mod XF square. This mod YF square is nothing but the output power spectral density SYF. SYF is equal to mod YF square, and mod XF square, that is equal to the output input power spectral density SXF into that is equal to mod XF square. So SXF, that is mod XF square, and SYF, that is mod YF square. They are the input and output power spectral densities respectively. So the relation between the two is SYF, that is equal to mod HF square into SXF. This is a very important relation. And the output power will be is obtained by integrating SYF over all possible frequencies. So PO, that is output power, that is minus infinity to infinity integral SYF df. That's equal to minus infinity to infinity integral mod HF square into SXF df. That's the way I compute the output power. Now let us compute the input, the impulse response of an LTI system governed by the equation dyt by dt plus 2yt, that is equal to xt plus dxt by dt. Taking Fourier transform on either side, it becomes j2 pi f into yf, because this is a derivative. So the Fourier transform is j2 pi f into yf plus 2 times yf, that's equal to xf plus j2 pi f xf. So yf becomes 1 plus j2 pi f divided by 2 plus j2 pi f into xf. So hf, the impulse, the frequency response is 1 plus j2 pi f divided by 2 plus j2 pi f. So h of f is 1 plus j2 pi f divided by 2 plus j2 pi f. I can write this as 2 plus j2 pi f minus 1 divided by 2 plus j2 pi f. That becomes 1 minus 1 by 2 plus j2 pi f. So the impulse response is the inverse of this hf. So inverse of 1 is delta t, and inverse of 1 by 2 plus j2 pi f is e raised to minus t ut. So ht is equal to delta t minus e raised to minus t 2t ut. Delta t minus e raised to minus 2t ut. Now consider another LTI system governed by dyt by dt plus 2yt, that's equal to xt, that is driven by the input xt equal to e raised to minus t ut. Let us compute the output. So since xt equal to e raised to minus t ut, x of f will be 1 by 1 plus j2 pi f. Okay, and here if I take the Fourier transform on the left side, it becomes 2 plus j2 pi f into yf. So that's equal to xf is 1 by 1 plus j2 pi f. So hf becomes 1 by 1 plus j2 pi f into 2 plus j2 pi f. Okay, So I can put this into partial fractions by taking the residues. Residue first I have to analyze both poles. So the pole for this term, that is f equal to minus 1 by j2 pi, and the pole for this term is f equal to minus 2 by j2 pi, 2 divided by j2 pi. So if I apply these poles here, I can use it with these poles. I can compute the residues of each term. So first pole for this is f equal to minus 1 by j2 pi. I can substitute f equal to minus f equal to minus 1 by j2 pi by masking this term. By masking this term means I multiply hf by 1 plus j with 1 plus j2 pi f. So if I put f equal to minus 1 by j2 pi f, f equal to minus 1 by j2 pi in this second part, it becomes 2 minus 1 by j2 pi into j2 pi. It becomes 1 by 2 minus 1, that's a 1. So the residue for the first term is 1. And the pole here, the pole for this term 2 plus j2 pi f is f equal to minus 2 by j2 pi. So if I apply that pole here, masking this term, if I mask this second term and apply the pole f equal to minus 2 by j2 pi here, it becomes 1 by 1 minus 2, that is j2 pi into 2 by minus j2 pi. It becomes 1 by 1 minus 2, that's a minus 1. So the residue for this term is minus 1. So so by taking residues you can very quickly compute the partial fractions. So it becomes hf becomes 1 by 1 plus j2 pi f minus 1 by 2 plus j2 pi f. What is this? This is actually the transform of e raised to minus tut, and this is a transform of e raised to minus 2tut. So I can compute ht as e raised to minus tut minus e raised to minus 2tut. So ht is e raised to minus tut minus e raised to minus 2tut. Now if the same system is driven by xt equal to ut, then yf will be 1 by 2 plus j2 pi f into xf is delta f plus 1 by j2 pi f. Okay, because xt is ut, its transform xf is delta f plus 1 by j2 pi f. If I multiply by both terms, it becomes delta f by 2 plus j2 pi f plus 1 by j2 pi f into 2 plus j2 pi f. Okay. Now this delta f x4 is 1 for f equal to 0 only. So what happens is this f j2 pi f term simply disappears because at f equal to 0 j2 pi f is 0. So it becomes delta f by 2. This term becomes delta f by 2, and the second term becomes 1 by j2 pi f into 2 plus j2 pi f, which I can easily put into partial fraction by taking the residues. So here there are two terms, j2 pi f and 2 plus j2 pi f. So this has a pole at f equal to 0, and this has a pole at f equal to minus 2 by j2 pi. Okay, so the residue of the first term can be found by putting f equal to minus for this term, the pole is f equal to 0. So if I put f equal to 0 in 1 by 2 plus j2 pi f, it becomes a 1 by 2. So the residue for the first term is 1 by 2. Okay, how do I find the residue? I put f equal to 0 in this equation by masking this term. Okay, so when I put f equal to 0 here, it becomes 1 by 2 plus 0, that's a 1 by 2. And I have to compute the residue here. So the pole corresponding to that is f equal to minus 2 by j2 pi. F equal to minus 2 by j2 pi is a pole for this one. So if I put f equal to minus 2 by j2 pi by after masking this term, this masking is equal to multiplication by 2 plus j2 pi f. Okay, but for the sake of for the ease of doing, we can think of masking that term. So here if I put f equal to minus 2 by j2 pi, it becomes a minus 1 by 2. So the residue here is a minus 1 by 2. So ultimately my terms, the three terms are, first term is delta f by 2 plus 1 by 2 by j2 pi f minus 1 by 2 by 2 plus j2 pi f. Now if I take the inverse transform, this becomes 1 by 2 ut minus 1 by 2 e raised to minus 2t ut, okay, because this corresponds to delta f plus 1 by j 2 pi f, that corresponds to ut, okay. This delta f plus 1 by j 2 pi f is the Fourier transform of ut. So this is my half of ut, because there is a half here, then this is a half of e raised to minus 2t ut. So this is half of e raised to minus 2t ut. So it becomes half into 1 minus e raised to minus 2t ut. When you come to the end, in this video you realize the output of LTI systems in frequency domain as product of Fourier transforms. Then you understood the input and output power spectral densities. Then you learn to analyze LTI systems with Fourier transforms. And that is the end of this presentation. I thank you all.